Question 9 from the 2018 Advanced Higher Physics Examination of the SQA. A ball bearing is released from height h on a smooth curved track as shown in figure 9a. The ball bearing oscillates on the track about position P, and the motion of the ball bearing can be modelled as simple harmonic motion, SHM for short. Part A, the ball bearing makes 1.5 oscillations in 2.5 seconds. And for 2 marks, we've got to show that the angular frequency of the ball bearing is 3.8 radians per second. Well, we go to Advanced Higher Physics Relationship sheet. We have the angular frequency omega is written as 2 pi times the frequency. And we know that the frequency can be written in terms of 1 divided by the period t. And the period t from here is the time for one complete oscillation. So we can rearrange the formula for the angular frequency as follows. Omega will become 2 pi, and that will be divided by t. And the units for that will be 2 pi radians divided by t in seconds will be radians per second. So all we have to do is find the period t of this motion, and we're told that 1.5 oscillations will take place over 2.5 seconds. So therefore one oscillation is going to take place over 2.5 seconds divided by 1.5, just doing simple proportion. So that comes out to be equal to, if we just leave it as a fraction, 5/3 of a second. So the period t is going to be 5/3. So period t is going to be equal to 5/3 of a second. And we can put that into the equation now. We can say it's going to be equal to 2 pi divided by 5/3 of a second. Remember, just leaving out units now for tidiness. So if we take the 3 up the top, we're going to have 2 pi times 3. And that's all going to be divided by 5. So we do that in our calculator. We have got the angular frequency omega, and that comes out to be about 3.77 to 3 significant figures, and the units are going to be radians, and of course that per second. But we can write that in 2 significant figures as angular frequency is 3.8, and it'll be radians per second. So that's the answer to part A, I. Part 2, the horizontal displacement x of a ball bearing from position P at time t can be predicted using the relationship x equals minus 0.2 cos of 3.8 t. Now, using calculus methods show that this relationship is consistent with simple harmonic motion. Well, to be consistent with simple harmonic motion, the acceleration of an object must be equal to minus a constant times the displacement x. That's the key factor in simple harmonic motion. Now we know the acceleration is the double derivative of the displacement with respect to time. So we can write down that d2 x by dt squared is going to equal to minus kx. So if we take a double derivative of x, that function x equal to minus 0.2 cos of 3.8 t, and it is equal to a constant, minus a constant, times the function x itself, then we've shown that it is predictable with simple harmonic motion. So let's start off with the formula itself. X is going to be equal to minus 0.2 cos of 3.8 t, and if you're quite observant, you'll notice that 3.8 is actually the angular frequency. Now, to find the derivative of that, it's going to be quite nasty, because we're going to be using sort of kind of like negative signs. So to make it easy for ourselves, we're going to let a constant, equal to minus 0.2. Just like that, equal to minus 0.2. And another constant, b, we're going to let that equal to 3.8. Just made up these constants, a to let it equal to minus 0.2 and b to become 3.8. So I can write the equation x as follows. A cos, and it's going to be bracket b times t. Remember, a and b are constants. Now that makes the formula for the horizontal displacement x a little bit easier to work with. So first of all then we take the first derivative, and I'll write it as x dot. X dot means dx by dt. So take the derivative of this function with respect to t, and we're going to end up with ab. And it's going to be cos, derivative of cos is minus, so it's going to be minus, and it's going to be sine bt. So really that's going to be the velocity at any given time of this motion. Now we take the second derivative, that's x double dot, and that's going to be the acceleration. So the derivative of this expression here is going to be minus a b squared, and the derivative of sine is cos of bt. And we can write that out as follows. We can write that in the following way. We can say it's going to be minus b squared times a cos and bracket bt. Now if you look very closely, the part we have a cos bt, that's just really equal to x. So therefore we have x double dot, the acceleration of the object, is going to be equal to minus b squared times x, because x is going to be equal to a cos bt. Now if you look very closely at that, then you can see that the acceleration of the object, that's what x double dot is, that's the derivative of the function with respect to time, finding the derivative twice of it, is going to equal to minus a constant, because b will be a constant, b squared will be a constant, times x, and that is very much the same as up here. We're going to have the acceleration equal to minus a constant times the displacement function x. So therefore what we've got here is simple harmonic motion. Question 9a continued. Determine the maximum speed of the ball bearing during its motion. This is for 3 marks. Now we already have this equation here, which we've got is the displacement x is equal to minus 0.2 cos 3.8 t, and we chose to let a represent minus 0.2 and a constant b to represent 3.8. We just invented these constants, a equal to minus 0.2, b equal to 3.8, so that we could write the displacement equation in terms like that. X was equal to a cos bt, because once it's written like that, we take away the sort of niggliness of the minus signs and make it easy for us to find the derivative. Because we know that the derivative of the x function, which is going to be dx by dt, is going to give you in fact the velocity, or the velocity in that direction. So the derivative of x equal to a cos bt is going to equal minus a, because the derivative of cos is minus sine. So it's going to be minus a, and it's going to be b, and it's going to be sine of bt. Remember, if you take the derivative of cos bt, it'll become minus sine bt, but you have to multiply by the constant in front of the t. So that's why we get the velocity to be equal to minus ab sine bt. Now we're asked to find the maximum speed. Now the maximum value of sine bt has got to be 1, because the sine function goes from 1 down to 0 down to minus 1. So the maximum value will be sine bt is going to give you 1. So for a maximum speed, then sine bt must be equal to its maximum value, which is going to be 1. So therefore the maximum speed, I'll write it as Vmax, is equal to minus AB, and you're going to have to multiply by sine BT, which we know is the maximum, is going to give you 1. So the maximum speed is equal to the two constants A and B multiplied together with a minus sign in front of it. So we plug those numbers in, minus, and A is going to be minus 0.2. So minus 0.2 multiplied by B, and B is 3.8. So we do that in our calculators. We have Vmax. It's just simply going to be a case of saying 0.2 times 3.8, and that's going to give us 0.76, and it'll be meters per second for speed. Here's the alternative way of doing question 9, relying on the Advanced Higher Physics relationship sheet. We have a section of it printed in the right hand side of the screen there. And the equation we're going to use is this one here. V equals plus or minus omega times the square root of a squared minus y squared. So if you've forgotten a moment how to actually get that speed from first principles, that's using the basic relationship here, y equals a cos omega t, or y equals a sin omega t, as shown there, you can always resort to this equation here. Now it's written in the y form, but we've got to change that to say that v, the speed at any particular moment, will be plus or minus the omega, the angular frequency, times the square root of a squared, and since we're dealing with the displacement in the horizontal x direction, we just change that to minus x squared. So we have already got the equation of the motion. That's x equals minus 0.2 cos 3.8 t, and we know we can write that in this form here. The amplitude A is minus 0.2 and the angular frequency omega equates to 3.8. So all we have to do is take that above equation there and remember this very important fact. And a very important fact is that the maximum speed, that's what we're looking for, occurs when the displacement is equal to 0. So that means the top equation, which we have here, will become the following. V max, the maximum speed, is equal to plus or minus omega, the angular frequency, times the square root of a squared, and x will be equal to 0, so a squared minus 0. And that just gives us the following relationship, plus or minus the angular frequency times the square root of a squared, and we know that's going to be equal to plus or minus omega times a, because the square root of a squared is a. So once again, we're just doing this simple little equation. To find the maximum speed, it's the angular frequency times the amplitude. So that's going to come out to be, we'll just keep the plus or minus in for the moment. Omega is 3.8 and the amplitude is going to be minus 0.2, so minus 0.2. So it's going to equal to plus or minus, and 3.8 times minus 0.2 is going to give us 0.76. So it's going to be minus 0.76. Of course, we just take the maximum value of that, which is going to be 0.76. And of course, the maximum speed will be measured in meters per second. So that's the other way of doing that, relying on the Advanced Higher relationship sheet and just working your way through it and working the constants. But it's much better to have a knowledge and a feel for what simple harmonic motion is and derive it from first principles. Part 4. Determine the height h from which the ball bearing was released, and this is for 3 marks. Well, we know from our previous answers that the maximum velocity occurs at this point here, p, and it's equal to 0.76 meters per second. Now to solve this, we look at the energy considerations. We look at the energy at the height h, and we look at the energy, total energy at position p. Well, when we're at height h, the ball bearing has only got potential energy. So at the top, we can say it has a certain amount of potential energy, mgh. When it gets to position P, it's going to have kinetic energy because its height above the position P0, therefore it's going to have no potential energy. So it's going to have kinetic energy. And what's more, if there's no friction forces which is going to soak up the any energy, the energy at the top, position H, will be exactly the same values as energy at position P. And we know at position P is going to be all kinetic energy, 1/2 mv squared. So that's the equation we've got. You can see that mass is on both sides, therefore we don't have to worry about it. The masses can be cancelled out and we're left with the following GH is going to equal to 1/2 v squared. Now we want to find h, so we divide both sides by g and we have the following. H is going to equal to 1/2 v squared and all divided by g. So we have all our data, so we can plug in the answers and see what we get. And that's going to give us 1/2, I'll put this in brackets for us, times v squared, 0.76 squared. I'm going to divide that by g, which is going to be 9.8. So we do that in our calculator, we end up with the value of 0.029 metres. And you can see that's equal to about 29 millimetres. So the height above the track will be about 29 millimetres. Question 9 continued, part B. In practice, the maximum horizontal displacement of the ball bearing decreases with time. A graph showing the variation in the horizontal displacement of the ball bearing from position P with time t shown in figure 9b. On the y-axis we've got the horizontal displacement from position P measured in metres, and on the x-axis we've got the time measured in seconds. And for 2 marks we were asked to sketch a graph showing how the vertical displacement of the ball bearing from position P changes over the same time period. Numerical values are not required on either axis. So we're going to be looking at the vertical displacement. Now the vertical displacement you can think of as the height above the point P. And you know that this is related to the potential energy, EP. EP is equal to mgh. Now we know mass is going to be constant and g is going to be constant, so therefore the potential energy is going to be linked to a constant times the value of h. And we can also say that the potential energy then is directly proportional to the height above the point P, which of course you can consider as a vertical displacement. Now, in order to see this happening in real life, we're going to go towards the PHET physics simulation site and see not a ball bearing in action but a skateboard in action, which is roughly the same thing we're seeing. So let's go straight across to the PHET site. And here we have it here, and you can see I've ticked the potential energy box. This is going to draw a graph over time of the skater's potential energy, which remember is linked to the height of the skateboarder above the ground. So we'll set it off and see what graph we do get. And you can see we're getting some sort of repeating motion, but the key thing to note here is that the peak of the graph is getting smaller and smaller as the energy is slowly diminished until it finally gets to about 0 there. We'll stop it there. So there's the graph you have of the vertical displacement, because vertical displacement is going to be related to the potential energy as we've shown here. And you can see the graph starts off at the peak here, the highest above the point P, and it goes through the cycle in a very same frequency kind of motion until it gets to this point here where there's no height above the point P. So really that's the sort of kind of graph that you are looking for. You're looking for a graph which starts with a peak, goes through a kind of sinusoidal wave, but the peak gets lower and lower as the skateboarder will not be returning to the original height that she left off at. So that's the sort of graph of the vertical displacement that you're looking for to answer this last part of this question.